start with it's 2 minutes past 4. Thank you very much for coming back. It gives me great pleasure to introduce Paul Cox, who's going to talk about modelling of biological and chemical. Paul.
Thank you very much. First of all, I'd like to thank the organisers for inviting me to speak to you this afternoon. It's a particular privilege to be involved in the session dedicated to Professor Thomas. By way of my tribute, I'm going to start my presentation talking about the area of one of his favourite topics, that of zeolites. I aim to cover modelling their structure and synthesis. In the second part, I'm going to move on to something a little bit different and look at the modelling of PETase enzymes. Currently, of course, of great interest in terms of recycling PET polymers. I hope that you see an intriguing synergy between these two seemingly different areas of science. I want to open my talk this afternoon by going back right to the first piece of work that I presented in public on modelling zeolites. Professor Thomas was in the audience and he spoke to me afterwards, but more about that later on. It's a good excuse, though, this to go back through an earlier piece of work and be able to say a little bit more about it now that confidentiality agreements have expired. So this particular work involved finding the structure of a zeolite, which was newly synthesized at ICI, known as NU87. And when I was first involved in this particular piece of work, they had a structure for it, which actually they'd optimized at the time using a program called DLS, which just tries to get all of the bond lengths to be a consistent distance. They knew that the model was very close to the correct one for NU87, but they knew there was a problem as well, because if they took the calculated X-ray diffraction pattern and compared it with their proposed structure, what they saw were the 6 differences, key differences that you can see there in the experimental structure at the top and the proposed structure at the bottom. And what I did here was to do energy minimization here using the program GULP, so based on interatomic potentials. And what we found, the structure at the top before minimization, after we minimized it, then we found a slight change in the space group there. You can see the difference in the detail around some of the bonds, particularly in the top and the bottom of the structure there. And a wonderful thing happened, because when we took that model from the GULP calculation and we calculated its X-ray diffraction pattern, all of those 6 lines which were missing suddenly appeared. So you can see them there, so you can see what a good job the energy minimization did of the structure, with the structure there. Very interesting material at the time. It had a unique 2D channel system that you can see here, and that was what gives rise to its unusual catalytic properties. At the time, ICI would not allow me to tell you where that template there sits in the structure. I think you can probably guess looking at it there. A few things just to say about its benefit to industry, this piece of work. So in terms of securing the patent, it was really important because obviously that mismatch in the lines was a cause for concern. But more importantly, and one thing that I was not allowed to say at the time, was that ICI thought that those extra peaks were due to impurity in the structure. So they actually had a whole team working on trying to produce pure NU87. And one of the great things, of course, is that this stops that completely unnecessary work. I well remember describing this work I had a meeting where Professor Thomas was in the audience. And one of the wonderful things which I always remember is him coming up to me afterwards, so much excitement and enthusiasm about the results. to me as a young researcher at the time, it meant an awful great deal. So amongst all the other wonderful traits that have been mentioned already about his scientific greatness, I'd like to add in that one as well, the encouragement that he gave to me as a young researcher just starting out. I also rather like, there's a book, Smart and More, a very good book on solid state chemistry, which quotes from a talk that Professor Thomas gave, in which he puts up the structure essentially of ZSM5, and he puts up a pattern which was on the wall of a mosque in Azerbaijan, and he notes and he says at the end of it, there is nothing new under the sun. And there's a rather nice postscript to the NU87 story, because all of that work that ICI put in and we put in to produce NU87, then a few years later, a geologist in Antarctica found NU87. So the natural zeolite counterpart. So all I want to add here is to say there is nothing new under the sun. A lot of my work here has been centered around looking at the location of templates or organic structure directing agents, whichever you would prefer to call them. And so we have used a technique generally that involves Monte Carlo placement of the templates within the structure, and then to use simulating annealing to heat up to a high temperature and let the temperature cool down to find the best locations for the templates. And that usually does a really good job of trying to trap out any local minima which may be there. So a very good way of finding global minima, particularly when you've got several templates within a structure. Again, one of our first successes, finding the location of the template in EU1. So hexamethonium sits very nicely in the side pockets of this particular structure. So we have a channel that runs through here with side pockets, and the template beautifully fills the side pockets. And again, one of the things I always like to do, work closely with experimentalists to try to use the modeling to help them with their experiments. Very successful, we've been over the years at predicting the location of our template molecules. And with EU1 here, on the left-hand side, we've got the pattern of the framework filled with the templates and also the empty framework as well. So at the bottom, we've got the difference between the two. So that's a contribution to the spectrum from the templates themselves. When we take the model there and put it in, then you see an immediate significant improvement in the fit here. And in fact, in that case, further Rietveld refinement didn't move the template at all. It agreed completely with the predicted location of the template. Relatively simple structures there. We've looked at more complex structures, one in particular, ZSM25. I remember when we optimized, when we did the GULP work on NU87, I had to get hold of the source code and change the arrays because of the number of atoms there. Well, there were just 300 atoms in the unit cell, I think, at that point. Here's a structure with 4,500 atoms in the unit cell, very complicated. But what we were interested in doing here is in locating where the TEA, the tetraethyl ammonium cations, are located within the framework. So there are seven different types of cage there. There are 5 which can realistically accommodate TEA within them. And so with the modeling, we looked at all of those 5 different types of cages and calculated the interaction energies. And what we found is that 2 of those cages had far better binding energies than the other 3. And it fitted together very, very nicely because We know that there are 40 TEA cations within the unit cell, and that if we added together the 18 and the 24 of these two different cage types, then of course that's very close to the target there of around about 40. So again, in terms of the refinement of the structure, if you put the templates in the predicted locations, then that was, again, gave an extremely good fit with the X-ray diffraction pattern. And perhaps more importantly, by understanding about the number of templates that went into which of the cages there, it was possible for the team working on these structures to produce even more complex ones, the isoreticular structures within this family, because they knew that cations needed to be added to create the smaller cages. And so knowledge about where the TEA cations were located helped them to work out the synthesis recipe for those more complex structures based on those smaller cages. Had a lot of work, a lot of success in terms of co-templating. So where we've taken cages and we've used different structure directing agents to produce each of the different cages within the structures. Now this work done in collaboration with Paul Wright's group has been very successful in producing new structures or making successful predictions for structure directing templates to produce particular cages. In this case, we're trying to find a template for the MER cage within the KFI structure. Several potential structure direction agents were looked at, and when we looked at the energies, there was one clear winner out of the 10 here, and it was that one which was used to produce the ALPO form of KFI, and indeed the other ones here, all of them, when they were tried, they completely failed to make that particular product. So really good in terms of the modeling being able to select the one for that particular cage type. And again, very good agreement between the experiment and the theory in terms of the prediction of the location for the template. We've already heard from Paul a little bit about the new SAPO materials that he's made. I will just add a little bit more about the modeling there, particularly in terms of the synthesis here of the AFX and the SFW structures. Again, the strategy here to take two cage types here, the GME cage here, or the AFT cage there, and the SFW cage, to make those particular cages and therefore those particular materials. In terms of the smaller GME cage, and again looking at several quaternary ammonium structures here, then if we go through these, then again there's one of the candidate structures, which are candidate molecules which came out at the top there. Very nice binding energy at the top, and a little bit of refinement of that to look at potential competing phases there, particularly with that template protonated or unprotonated, led us to conclude that the best one to use here would be the trimethylamine at the top left there. So very nice fit in the cage, very good binding energy. And then to take the DABCO units to try to predict what would make the AFX and the SFW cages there. So we can see the smaller chains here between 3 and 6. We certainly got a very nice fit in the middle there. And when it comes to SFW, then in particular at around about 6 and 7, we can see a very nice fit in the cage there. Again, that's borne out by the binding energies which we produced. So again, you can see the lower numbers here consistent with good energies in the AFX cage. And then when we get to the larger ones here, 6, 7, and 8, they favor that SFW cage there. Successful synthesis, again, at the predicted locations. And again, the modeling was used as a starting point for the Rietveld refinement here, in which we have AFX here, formed with the DABCO C4 and the trimethylamine template in the GME cages, and again, SFW. And the nice thing about the SFW, that was done completely before the experiments took place. The suggestion, try the C6 template there, was done before any of the synthesis took place. So a real prediction there that came to pass. Always expect surprises when you're making zeolites, perhaps is the message here, because one of the things that Paul's group found was that you can use the C6 template, you can use the trimethylamine, and you can make a completely different structure here, that of STA20. And you may look at this structure here, and it's quite nice. They synthesized it, and then they found the X-ray pattern matched one structure from a theoretical database. So structure was solved in that way. But how about the templates here? Because we have the two different types of cage, and we have the STA cage here, which is much longer than the SFW cage that you saw earlier, which the C6 template fits really nicely into. So again, we looked at the modeling of that, and you can see that if you put the C6 DABCO template into that STA20 cage, it looks a bit short. The energy certainly seems okay. In fact, it's slightly better than the template in the SFW cage, but the key thing is there's a bit more air, a bit more volume in there. And so one of the things you think is, well, are there trimethylamine templates in that cage as well? And there seems to be just the room for one of them to fit in alongside that C6 template, the DABCO one there. What is very interesting, and you very often see these patterns and they're repeated, despite having a different molecule at the end here, when you view from either end of the cage, you see the same pattern there. So the orange one is the trimethylamine, and here we've got the DABCO C6. But if we put the two templates into the case there, the energy improves quite significantly by 11 kilocalories per mole. You may think, and I would certainly look at that and think, well, there's symmetry here. Surely there must be another one at the other end of the cage. But when you do the modeling and you put that in, then suddenly you've got too much in there. Everything is too close. The binding energy plummets by 84 kilocalories per mole, and you can see the distortion of the C6 template in the middle there. So modeling suggests just one template in there, one of the trimethylamines in here, alongside the C6 template there. And again, that is what is borne out from the X-ray diffraction. And again, the best fits there come from the model with just a single additional template in that STA20 cage. Again, STA28, just very quickly, a few other things to add to what Paul's already said about this in terms of the modeling. So it's a very interesting one because you have the template here covalently bound to the framework, which is quite unusual here. And if we use a DFT approach, we can look at the template within the structure. We'll have more of a look at that in a moment. One thing we were able to do there, modeling, which was helpful, was that if you take the template out, then the aluminium here, or as been said, the iron there, will then go from 6 coordinate down to 4 coordinate. And what we're able to do there was to model what the structure would be like with that 4 coordinate aluminium there. And what is interesting from the energies here is that when you compare it with other ALPO type structures, then you see something which is significantly less favorable. So that strong covalent bond there with the template seems to play an important role in stabilizing what might ordinarily be a difficult structure to synthesize. Again, it's interesting if we look at the template, this case here with the ion in place there, which is directed to that site in the synthesis. We look at a smaller template here, the 2,2 bipyrimidal molecule here. Doesn't fill the space anything quite like as well. You've still got that 6-fold coordination there, but the experiments show that you don't form it with this particular molecule here, and the calculations suggest it is less stable by 14 kilojoules per mole. So it's still really important that you've got that 6 coordinate there in the structure, but you've also got good van der Waals interaction with the rest of the structure there in order to stabilize it and form it. And again, in terms of DFT calculations, we're able to optimize the structure in terms of the location, the geometry around the ion at that 6 coordinate site. What happens when we take the template away and leave it 4 coordinate there, then this is the prediction from the DFT. Again, good match with the experimental X-ray diffraction pattern, and again used as a starting point in terms of the solution. One final thing to just mention in terms of zeolites here is a little bit here about organic free synthesis here of the structure ZK5, which is very interesting. It comprises of 2 different types of cages here. There's no organic used in the synthesis here. The synthesis is driven by the inorganic ions which are used within the synthesis mixture here. So the structure, again, of course, known, but what the modeling was used to do was to predict the location of the cations and the anions within the framework. And what is really fascinating here, I think, is that when you look at this, within, for example, the larger LTA cage here, those cations and anions order together to fill the space within that cage very nicely indeed. And it's very interesting because if you plot out the electrostatic map of the LTA cage, you can match it almost perfectly. So the cations here correspond to the red regions which are highlighted in that electrostatic map. The negatively charged ions are in the locations predicted by the blue that you can see there. So, moving on from zeolites now to something else, because one thing that we're interested in at Portsmouth is looking at enzymes which are involved in breaking down PET, the polymer, which of course is associated with plastic drinks bottles, etc. And of course, what we want to do here is to be able to take our plastic waste and then design and use enzymes which are going to break down the polymer into its monomer building blocks so that we can then recycle those building blocks and make new plastic products from them. At Portsmouth, a lot of work has been done at trying to generate new enzymes. This work, known as Project 74, identified 74 novel enzymes potentially can break down PET. They used bioinformatics and machine learning to try to find these brand new PET hydrolases. What is really interesting, again, it was very fortunate because at the time that this work was done, the 2T sequences were found, and then fantastically, along came Google DeepMind with AlphaFold, and we were able to use that program to solve essentially the 3D structures of all of those 74 enzymes. So what we wanted to look at was how the PET fragments would fit into those enzymes. And so we've used basically a molecular mechanics docking type approach that traditionally used in terms of drug docking and drug design to look at some of the more interesting cases here. And one thing just to point out to you before I show some structures is that in terms of the breakdown of the PET, one of the first things that needs to happen is that the carbonyl group within the polymer needs to be close to the serine, which is part of the catalytic triad within the enzyme in order to start that process of the breakdown. So we use a docking approach. I actually skipped from that, I was looking at the time, but let's first of all look at a well-known PETase. So this one, LCC. And this shows you one of the problems with the enzymes which work well, because what we're looking at here is the rate at which the enzyme breaks down amorphous PET compared to crystalline PET. And we see something very different here. This enzyme breaks down amorphous material really quickly, but crystalline material very slowly. And in fact, a lot of people said, well, you won't get the enzymes to work. They work on amorphous material, but they don't work on crystalline material. Let's have a quick look at the docking location for the PET trimer here within LCC. The orange here represents the binding pocket that trimer binds to here. And what we can see here is we can see that lovely binding pocket there in the center, which is just the shape of a monomer of the PET. But if you look at the two units next to it, you can see that they have to effectively rotate at 60 degrees to the central one here in order for that carbonyl group in the middle here to get close to the serine unit within the enzyme. And there it is shown just in single view there. Here is the serine, here is the carbonyl up here, or carbonyl there. And you note that the two rings here have to flip kind of to enable that to happen. And there's the binding pocket. I hope that makes sense. So we see a distinct hump, for example, here. That is quite a deep pocket there for the monomer to drop into. Let's look at one of the interesting things which came out of Project 74. One of the enzymes here, when they looked at it, we find the reverse. We find that this enzyme here, 611, is great at breaking down crystalline material and not the amorphous material. So why is that? And if we look here, then what we can see here is we have a binding pocket which is much flatter, much straighter. The polymer, when it binds in there, if you look at it down from here, you can see that the arrangement of those benzene rings there is very different. They are both aligned in the same direction. So binding site, you can see particularly from this view here, it is very straight, much straighter. But if we think about the crystal structure here, of PET, look at how those chains are orientated. If we take a single chain here, we can see that those rings are orientated in the same direction. In fact, that looks, of course, very like how it looks inside the enzyme 611 there when you look down from the top. So it seems that the environment around the binding pocket here is what is really significant. If you have an environment where the active site is relatively flat here, then it allows the rings to go into that binding pocket in the same orientation, and hence we speculate that it is much better with this in terms of breaking down the crystalline material rather than the amorphous. And there you can see the whole enzyme there. There is the binding pocket, nice and straight, which that polymer there can just nicely slot into. Another example, 504, very similar, just run through this quickly, looking at the clock. But there you can see a preferred energy minimized configuration of the molecule of the dimer, in this case, docked in here. And you can see that around here, we've got a raised area here, which is going to effectively stop that ring here from spinning round. Or more than that, if it's trying to dock in there as an amorphous polymer with rings at different angles, it is much less likely to dock in than if it is in that straight kind of crystalline sort of orientation. Okay, and an example there of 601 here. 601 is quite nice because it's good at breaking down both of them. And here we can see it has the ability here to accommodate chains within the active site here, which are both flipped and both straight as well. So one which is equally good at both, appears to be good at accommodating both of those different orientations in terms of the rings within the polymer. And again, just to go back to LCC, you can see if we actually just try and dock in a rigid train, that what we find is that where the serine is here, that our carbonyl group is a long way away because it can't get down into that binding pocket if you have got a straight chain there, and the lengths are such that it just can't do it. It can't bridge it, it can't dock in there. It has to bridge across in order to dock over the top there. So it makes you wonder in terms of the way forward, in terms of producing enzymes which will be more effective in terms of crystalline PET, then we've got to think about the environment around that binding pocket. For example, with LCC, can we alter the residues of the enzyme around here to make it flatter so that it could be used for both amorphous and crystalline materials? A lot of work to do here to fully understand this. We want to, of course, understand about how this interacts with the crystalline surface here, the surfaces of the polymer. But again, it's some very interesting things to be done there to try to fully understand what's going on here and to try and modify and improve these types of enzymes. So just to conclude, I think I've just about made it on time here. But in terms of the zeolites, just to, what I hope I've highlighted here is the important role that modeling plays in conjunction with experiment. And of course, that was one of John Thomas's great legacies, really, that the modeling here can be used to make good predictions here, but things are always complicated, as we saw with STA20. It's not easy always to understand exactly what's going on, and that's why predicting new templates is so difficult. And there, in terms of the enzymes, I hope you could see there what we're thinking in terms of the difference in particular here in terms of being able to break down the crystalline PET versus the amorphous PET and the importance of the surrounding area around the binding pocket within the enzyme. Finally, just a few very important acknowledgements, particularly to Paul Wright. Thank you very much, Paul, for all the work that we've done over the years. Thank you to, and his group as well, some of whom I've highlighted there. Johnson Matthew as well, particularly Alessandro and John and Mervyn, have been great to work with for many years. I'm back at Portsmouth, James Matter, but in particular people associated with the CEI at the moment, so John and Andrew. Thanks very much.
Paul, thank you very much indeed for a great talk. We've got a couple of minutes for questions. David?
Thank you.
I think of these like grazing enzymes, so like grazing cattle on. But what do you know about the rates of the reaction?
Well, it's interesting because I tried to learn that relatively, in terms of how fast are they as enzymes, they're not as fast as your average enzyme is, relatively slow. So there's a lot of work that we can do to improve those rates. But we are, of course, very, very tantalizingly close to these things being used commercially. So they're fast enough to be a commercial proposition. I think that's one of the key things.
Okay.
So my question talks about obviously all your studies around the relative geometry of the binding of the PET into the SAPO, but presumably there are other facets of those enzymes that differ in terms of the structure, the chemical structure around the PET. So I don't know whether your modelling is capable of looking at that as well around the acid base.
Yeah, very well. Not the whole story by any means. There's a lot more that we can look at here. But to me, there does seem a really telling argument here that says, in terms of, for example, just looking at amorphous versus crystalline, there's that really real shape relationship, which I think makes a great deal of sense without looking too much further in terms of detail. I think probably what's really important is to go on and look at how they interact with surfaces rather than just change. Because
Sure, yeah.
you want to know, I mean, there's so much more you do need to know. I mean, I would say we need to know how they bind, but we also need to know what happens in terms of the removal of the monomer. I think that's a really important step for us to understand, because it seems some of the residues close by are very important in terms of the release mechanism once the monomer has been broken off.
Okay, I think in the interest of time, I think we'll move on. Thank you very much indeed, Paul.